Hello, and welcome to the third lecture of our Physics 1000 course. In this lecture, we'll be discussing the physical quantities of force, mass, and weight, the concepts of Newton's three laws of motion, inertia, and friction, and we're going to see how we add vectors graphically, along with how to draw a free body diagram. And so to get started, I'm going to introduce the physical quantity of mass. And so most people, I think, are familiar with mass, right? It's the measure of the amount of matter, okay, that an object has. And not to be confused with weight, we're going to talk about weight today, but mass is the amount of matter contained in an object, and the standard unit of measure for mass is in the SI system is the kilogram, right? And so a smaller unit would be a gram. And so mass is, the larger an object is, typically the more mass it has. Right? A bowling ball has more mass than a volleyball. Now, when it comes to motion, mass is important because it turns out that objects, they don't like to change the way that they're moving. And that resistance to a change in their motion is known as inertia. And you might have heard that term before too. Inertia is a resistance to a change in motion. Okay, so in other words, if an object that is at rest, and it's not moving, it doesn't want to start moving. It doesn't spontaneously start moving. Why? Because it has inertia. Inertia is that resistance to start moving if it's at rest. If an object is moving, it's moving at a constant velocity. Remember from our last lecture, velocity has both speed and direction, so it's moving at the same speed, that's the magnitude of the velocity, and it's not changing direction. Then because of inertia, that object wants to continue traveling at that same speed and direction. It doesn't want to change speed, doesn't want to speed up or slow down, it doesn't want to change direction because the object has inertia. Now how mass ties in is, mass is the inertial property of an object. Basically, it's an object's mass that gives it inertia. The more mass an object has, the more inertia it has, the more resistance to a change in motion. And so if we think about this from our everyday life, we could probably relate to it, right? It's harder to get something to start moving if it's more massive than if it's lighter, right? The bowling ball, if we want to get a bowling ball moving, it takes more effort than that volleyball I mentioned earlier. Why? Because the bowling ball has more mass, therefore it has more inertia. Conversely, if say a bowling ball is moving and we want to stop it, right? That's still a change in motion for stopping it. Say if someone's passing us a bowling ball, it takes a lot more effort to catch and stop that bowling ball than it does the volleyball because of the difference in inertia. Now, so we now have an understanding of mass and inertia and how they're related, right? It's the mass of an object that gives it inertia. That what we just discussed is basically Newton's first law of motion. Newton's first law of motion is also sometimes referred to as the law of inertia. And Newton's first law of motion states that, Newton's first law, it states that the velocity of an object remains constant. Remains constant unless an unbalanced force acts on the object. So in Newton's first law, it states that if an unbalanced force does not act on an object, that object's velocity will remain unchanged. It will remain constant. At rest is a velocity, right? It's a velocity of 0. So if an object is at rest, that velocity of 0 will remain 0 unless an unbalanced force acts upon it. If an object is moving with a non-zero velocity, so it has a given speed and direction, it will continue to move at that speed and direction, in other words, that velocity, until an unbalanced force acts upon it. That's Newton's first law of motion. It's basically telling us what inertia, right? An object has inertia. It doesn't want to change its velocity unless it's forced to. Now, we've introduced this new term, force, right, in Newton's first law. An object's velocity remains unchanged unless an unbalanced force acts upon it. So, what is a force? Right? That leads us to our next physical quantity, which is a force. So a force, you could think, it is something that can potentially change motion. I say potentially because forces could act on an object and not change the motion, because there's this qualifier of unbalanced, which we'll discuss. But a force is a push or pull on an object. So if I push against this wall, I'm exerting a force on it. Right? If I pull on this board, that's a force. Any sort of push or pull is a force, and there's in the universe as of now there's five types of forces. There's these nuclear forces. There's gravity, gravitational force. There is electromagnetic force, electric force, and there's a magnetic force. Right, those are the 5 fundamental forces. And like you said, well, what's this? Push or pull? Well, we're interacting the electrons and protons of the atoms that make up us are interacting with the electrons and atoms that make up the other object that we're in contact with, and so those are electrical charges. So it comes down to the electrostatic forces. But just a little conceptual interlude there. A force is a push or pull, and we can kind of group those forces into 2 types: contact forces and non-contact forces. So contact forces are forces that objects exert on each other when in contact with each other. So for example, I'm holding this pen, my fingers are in contact with it, and they're exerting a force on it. My hand is exerting a force on this pen is exerting a force on my hand, because they're in contact with each other. Non-contact forces are forces that objects exert on each other, as you might guess, when they're not in contact with each other. Examples of non-contact forces are gravity, right? Earth can exert a gravitational force on us without being in contact with us. Right? So if I let go of this pen, it drops down to the earth because the force due to gravity, Earth's gravity, is pulling it towards the earth. And so while this pen's in the air, it's not in contact with the earth. That's a non-contact force. There's the electrostatic force and there's a magnetic force. Those are also non-contact forces. So there's contact forces and non-contact forces. Now force is a vector quantity. Which means it has both magnitude and direction. Correct? So if I push on something, there's a direction I push on it. I'm pushing on it into the board. So that's the direction, and then there's the magnitude. It's how hard I push. If I pull on something, I pull on it in a certain direction, right? That's the direction, and then how hard I pull is the magnitude. So force being a vector quantity, it has both direction and magnitude. And so when we go back to Newton's first law, it says an object's motion will remain unchanged. Basically, its velocity will remain constant unless an unbalanced force acts on the object. And so unbalanced suggests that that there is a state where there's balanced forces. And balanced forces is whenever there's multiple forces acting on an object, but they all cancel each other out so that they're balanced. And the net force acting on the object is zero. And so how we get an idea of how forces can balance each other out or be unbalanced is we have to add them together. And because, I just covered up, because force is a vector quantity, to know how to add vectors together, at least conceptually for now. Because vectors don't add together simply arithmetically like other quantities do. Like if you want to add mass together, 5 kilograms plus 2 kilograms, that's simple, 7 kilograms. Vectors don't add like that. Because they have not only that magnitude, but they have the direction. So how do we take the direction into consideration? So let's say we have a force F1. Okay. Well, let's not do forces. Let's do maybe displacements. Right? We have a vector A, which is equal to 5 meters in this direction. And let's say we have a vector B, which is 2 meters in that same direction. Now we want to find a vector C that is the sum of vector A plus B. So how we add vectors graphically is we draw the vectors where the length of the arrow is proportional to the magnitude. So you'll see that this is 5 meters and this is 2, so that's roughly 2/5 of the length of A. Now that's just probably not exact, just my best eyeballing it. And whenever we add vectors, we draw the first vector. Alright, and then so I'm going to draw vector A. And then where vector A ends, the tip of it, that's where I begin the next vector, B. So I put the tail of B at the tip of A, and I draw it. And so you add vectors tip to tail. You connect them together. And where, starting from the beginning of A to the tail of A to the tip of B, that is vector C, the sum. And so vector C in this case would be 7 meters in that direction. So, well, that's just 5 plus 2, right? I thought you said you just can't add them like that. This is a special case where the vectors are pointing in the same direction. Right? Now, vectors they do add commutatively, which means the order doesn't matter. right? If A plus B equals C, then vector B plus vector A should also equal C. And if we start with B and we add on A, yes, we do get the same vector C. Okay. Let's do a different example and see how vectors differ than adding just normal numbers. Let's say that vector B is 2 meters long, but now it points in that direction. All right. So vector A plus B, we're going to find vector C, so draw A. Now from where A ends, we draw vector B, and then where we start with A to the tip of B, that is vector C. So this is vector C right there. And its length should be 5, and then 2 should be 3 meters. Alright. So we see because B is going in the opposite direction, it kind of doubles back on some of the distance or sum of A. So sum of A is being canceled out by B, or you could say that all of B is being canceled out by a portion of A, because they're in opposite directions. And like we said before, it's commutative, right? So B plus A should equal C. So if we draw vector B first, and then draw vector A, we start from where B started to where A ends, and that's vector C. That's that same vector, right? So it doesn't matter the order. So if the vectors are going in opposite directions, they counteract each other to some extent. So now you can see about those balanced forces, right? If forces are acting in opposing directions, they can counteract each other or cancel out some of each other. And forces can be pointing in directions and have magnitudes in a way that they completely balance each other out, so that there's no net force acting on the object. So let's look at another example. Now let's say vector B points this way now instead. It's still 2 meters. So vector A plus B equals vector C. We draw A, and we add on to A vector B. And so going where A starts to where B ends, we have vector C. Now how long is vector C? Well, because A and B are perpendicular to each other, this makes a right triangle. So we can use Pythagorean theorem. Pythagoras' theorem. So the length of A squared plus the length of B squared equals the length of C squared. So the length of C is the square root of A squared plus B squared. We can get the length of C that way, only because vector A and B are perpendicular to each other, and this makes a right triangle, right? If vector A and B are not perpendicular to each other, we can't calculate the length of C that way. Okay, but because they are perpendicular to each other, you can find the length of C that way. Once again, it's commutative, so B plus A should equal C. B plus A gives me the same vector C. All right. Now, if we add multiple vectors together, more than 2, that is. Let's say we have a third vector. Let's say vector C is, let's make this 4 meters. Now find vector A plus B plus C equals some vector D. Well, draw vector A, then vector B, then vector C, and vector D. We go from the beginning of A to the end of C. That would be vector D. Okay. So we add vectors, it said tip to tail, where we begin with this first vector, where it ends, the next vector starts. And where that ends, the next vector starts. Now, that's adding vectors. subtracting vectors is the same as adding vectors. Okay. So if we do vector A minus vector B equals some vector C, we start with A. But remember, in math, using mathematics, we denote the sign using a positive or negative, which direction, right? If that's the positive direction, then the vector in this way is positive. That's the negative direction, the vector that way is negative. So the arithmetic sign, positive or negative, indicates the direction of the vector. So if we change the sign of a vector, we're changing the direction, right? And this negative, A minus B, could also be viewed as A plus negative 1 times B. And so when you multiply something by negative 1, you're just changing the sign. You're making it from a positive to a negative, or from a negative to a positive. So we're adding vector B, but just in the opposite direction. And so I draw A. I draw vector A. Instead of adding B, I'm going to add B pointing in the opposite direction. So this is negative B. And so this is vector C. Now, unlike addition, subtraction is not commutative. So this does not equal B minus A. You can't flip it. Because B minus A would be, this is B, and then this is minus A. We get C. But you'll notice that C, this C, is equal to, this is negative C. This is C. So what we do get is the same vectors, same length, C, but just pointed in the opposite direction. That's why it's a negative. So we can say it is equal to negative 1 times this quantity, which is negative C. Because negative 1 times this gives us A minus B. If we distribute that negative 1, so this becomes negative B, that becomes a positive A minus B. But we cannot say A minus B equals B minus A. That doesn't work for vectors. That doesn't work with normal subtraction. So 5 minus 2 does not equal 2 minus 5. So subtraction is not commutative like addition. All right, so that's how we graphically add vectors, at least conceptually. And so if we have multiple forces acting on an object, so let's say we have an object, we have a force F1 acting that way, and a force F2 acting this way. And let's say F1 and F2 are equal magnitude, but they point in opposite directions. Then we say the net force, the total force that's acting on the object, is equal to F1 plus F2. And so if we add them, we have F1 plus F2, we get this point, right? It comes back to the same point, and that has a magnitude of 0. So they cancel each other out. So these forces are balanced, and it's 0. So even though forces are acting on the object, it has a net force of 0. The forces are completely balanced, and so this object will not start to move if it's not moving. If it is moving with the velocity, its velocity will remain unchanged because there's no unbalanced force acting on it. All right, and according to Newton's first law, an object's velocity will remain constant as long as there's no unbalanced force that's acting on it. So I just want to make that clear that forces can be acting on an object, right? And it could still maintain a constant velocity because those forces are balanced. If, however, say F2 was, say, half of F1, now if we add those vectors together, F1 plus F2, then the net force is not equal to 0, right? It's going to be like 1/2 F1. And so there's going to be a net force in this direction, and so the object's velocity is going to change. Okay? So it's going to change the object's velocity if there is an unbalanced force, a net force. And so that brings us to Newton's second law. So Newton tells us, all right, if there's no net force, if there's no unbalanced forces acting on an object, its velocity remains constant. Its motion does not change. Newton then told us, well, what happens if there is an unbalanced force? If there is a net force on its object, Newton's second law tells us how its motion is changed by that unbalanced force. So now we know how to add vectors graphically. I'll check that off. So Newton's second law basically, let me write this down. Says that if an object's velocity changes, then the object experiences an acceleration. Because remember that this is a little side note, that acceleration is change in velocity over change in time. And so if an object's velocity is changing, then that means it has an acceleration. And that acceleration multiplied by the amount of time it experiences that acceleration for gives us what the change in velocity is. So if there is an unbalanced force, if there is a net force acting on an object, that object is experiencing an acceleration. And so if an object is experiencing acceleration, that means it's experiencing a change in motion. And the acceleration is proportional to the net force acting on the object. So proportional means that they go one and one. They go hand in hand, right? If I increase the net force, then I increase the resulting acceleration the object experiences. If I decrease the net force, then I decrease the acceleration that the object experiences. All right? And the acceleration is proportional to net force and in the same direction. Okay, so, but that says if the net force is, say, in this direction, so the sum of all forces acting on the object is in that direction, then the corresponding acceleration is also in that direction. So the acceleration that an object experiences from a net force, from unbalanced forces, is always in the same direction, points in the same direction as that net force. All right, so as we increase the net force on an object, we're going to increase its acceleration, right? If we, and the acceleration is in whatever direction that net force is pointing. But that's not it. There's something else. We go back to Newton's first law that objects don't like to change their motion. They have inertia. And so if a force is going to change a motion, change the motion of an object, give it an acceleration, the inertia resists that change. Okay? And so the acceleration that an object experiences is inversely proportional to the mass of the object. And inversely proportional, what that means is the greater the mass of the object for a given net force, the smaller the acceleration. So if we have a net force acting on an object that has a big mass, the acceleration it experiences is going to be smaller than if we have the same net force acting on an object with the smaller mass. And so we write this mathematically as A is proportional to this. This is the Greek letter alpha, which is proportional to F net. And mathematically, we represent this A is proportional to 1 over mass. Because if mass is a really big number, 1 divided by a big number gives you a small number. If mass is a small number, 1 divided by a small number gives you a big number. So they're inversely proportional. So the smaller the mass is, the larger the resulting acceleration from a given force. The larger the mass is, the smaller the resulting acceleration is for a given force. Now, Newton's second law combines these two relationships between acceleration net force, acceleration in mass into one equation, arguably one of the most important equations in science. This equation is used all around us to engineer the world around us. Anything that has moving parts, at least, and that is acceleration is equal to the net force applied on an object divided by its mass. And so there you can see the direct proportionality between acceleration for net force. The larger net force is, the larger acceleration. And the inverse proportionality between mass and acceleration. The larger the mass is, the smaller the acceleration. The smaller the mass is, the larger acceleration. And this is often rewritten as F net equals mass times acceleration. This is Newton's second law. This is going to underpin almost the entirety of the rest of the semester on this course. One of the most fundamental and important concepts in science. Newton's second law. Now, I want to stress that this is empirical, which means that it's true. We just observe it to be true. We don't know why, right? We don't know why the net force exerted on an object is equal to its mass times acceleration. No one has come to that answer. And if you answer that question, you'll probably win a Nobel Prize. And you will enter in the halls of fame with Newton, Einstein, and all the other great thinkers in science throughout history. But we don't know why this is true. It's just observed to be true. So it's an empirical observation. And so this is Newton's second law of motion. It basically tells us, it plays off of Newton's first law, in that if an object, if there's no net force on an object, the object's not going to change its motion. Its velocity is constant. Because if F net is equal to 0, if it's balanced, then acceleration equals 0. No change in motion. However, if F net is not equal to 0, then the resulting acceleration that the object experiences is equal to the net force divided by the mass. And mass is not a vector. It only has magnitude, no direction. Force is a vector, and acceleration is a vector. And so in order for this side of the equation to equal this side of the equation, they both have the same magnitude, and at the point in the same direction, so that tells us that F net and acceleration have to both point in the same direction. So if we draw these vectors, this is vector A, and this is vector, same length, F net divided by m. So this number must equal that number, and their directions must be the same. Another way of looking at it, if this is F net, then this is ma. Same length, same magnitude, same direction. So, with this, we can come to some idea of what the units of force are. Because if force is equal to mass times acceleration, then the units of force are going to be the units of mass times the units of acceleration. So the units of mass are kilograms, times units of acceleration, meters per second squared. So these are the units of force, kilograms, meters per second squared. But we use force so much in physics that this is cumbersome to always be writing kilograms, meters per second squared. So we define this as its own unit. It's a derived unit. Remember, a derived unit is a unit that is a combination of fundamental units, in this case mass, distance, and time. 1 kilogram meter per second squared is known as 1 Newton. 1 Newton, named after Isaac Newton, and we use a capital N to abbreviate the units of newtons. So newtons are the units of force, and 1 Newton is 1 kilogram meter per second squared. And so, if we look conceptually, if we have an object, if we exert a force, one force, F1 on it, and it has a mass m, it's going to experience an acceleration in this direction that's equal to F1 divided by m. If we double the force, F2, which equals 2F1, same mass, then the resulting acceleration is going to be doubled, because it's going to be, the acceleration is going to be F2 over m, which is 2 times F1 over m, because F2 is equal to 2 times F1. So if we double the force acting on it, the same mass, the resulting acceleration is doubled. Likewise, if we had half the force and keep the same mass, we would half the resulting acceleration. What if instead of changing the force, what if we keep the same force, but now we're doing twice the mass? We exert the same force on twice the mass, well then the acceleration is halved, right? We get 1/2 of this original acceleration. So if we double the force, we half the acceleration, which shows that inverse proportionality of acceleration and mass. The more mass, the smaller the acceleration. Double the mass, we half the resulting acceleration. Right? So that's Newton's second law. Force equals mass times acceleration. Extremely, extremely, extremely important equation in physics. So, now we're going to move on, discuss force, to talk about weight. Now, weight is a type of force. It's a so there's a lot of different types of forces, and we just give names to different. I guess you should say it's a common force, and we give names to different common forces. But weight in general is the force due to gravity on an object. So an object's weight is the force due to gravity acting on an object. That's its weight. So if we have an object, it's, say, sitting on a scale, it has a mass m. What is its weight? Well, the weight is the force due to gravity acting on it, which we can just call it its weight. Maybe we just use W, capital W. Well, we know that force is equal to mass times acceleration. That's what Newton's second law tells us. Well, what acceleration does gravity exert on an object? Well, every object that, at least on Earth, that's in free fall or is allowed to free fall experiences the same acceleration. And the acceleration due to gravity, which we introduced in our last lecture, on Earth is G, we represent with G, which is 9.8 meters per second squared, and always points downward. So the force due to gravity, which is its weight, is equal to the object's mass times the acceleration that gravity is causing, G. So mass times the object's mass times its acceleration due to gravity gives us the object's weight, which is the force due to gravity on the object. And this side of the equation, weight, is a force. This side of the equation is a vector. It's also force, mass times gravity. But the magnitudes have to be the same, and they have to point in the same direction. Since gravity points down, the weight points down. Weight always points straight down toward Earth. So weight is the force due to gravity. And that's why sometimes weight and mass get confused, because they're proportional to each other. All right? See, the larger the mass is, the larger the weight of the object is. The less the mass, the smaller the weight of the object. And we're going to discuss where this equation comes from. I mean, it is Newton's second law, but we're going to see that there's more fundamental physics behind it when we talk about gravity. So an object's weight is its mass times the acceleration due to gravity, right? And it always points straight down. Straight down. So now, this is the object's weight on Earth. If we wanted to find an object's weight, say on Mars, you have to take the object's mass times the acceleration due to gravity on Mars. Okay, so whatever the acceleration due to gravity is on Mars, multiplied by the mass, it gives us the object's weight. So that's why it's better to report an object's mass than an object's weight, because an object's weight is subjective to the gravity that it's being subjected to, whatever planet it's near. So an object has a different weight on the Moon, on Mars, on Jupiter, on Earth, but it has the same mass. It has the same mass everywhere. So that's the difference between mass and weight. Mass is the amount of matter, where weight is a force. It's a force due to gravity on that object with the matter, with mass m. Okay. And it always points directly downward. Okay. Now that we have discussed weight, we're going to move on to Newton's third law, which colloquially you've probably heard of. For every action, there's an equal and opposite reaction. That is a common way of saying Newton's third law. In particular, Newton's third law, it reads as, if an object exerts a force on a second object, the second object exerts an equal and opposite force back on the first object. So objects exert equal and opposite forces on each other. That's if they're exerting any force on each other. Equal is the magnitude, how strong the force is, and opposite is referring to the direction. So if this is object 1, this is object 2, this is the force the object 1 exerts on object 2. So whenever we're drawing forces acting on an object, we draw the force starting from the object that the force is acting on. So this, and then in this notation, the first item here in the subscript is the object that is exerting the force, and And the second is the object that the force is being exerted on. So you can read it as the force of 1 on 2. Force of object 1 on 2. And we draw it coming from object 2. So here, this would be the force of object 2 on 1. Now they're equal in magnitude, right? So we say force of 1 on 2 is equal to force of 2 on 1, but we've got to put a negative sign in there because they're opposite directions. Right? So they're equal in magnitude but opposite directions. That's Newton's third law. So if I basically push on this whiteboard with a given force inward, Newton's third law tells me that the whiteboard exerts a force back in the opposite direction of the same magnitude, the same strength. That's true with any type of force. So remember I said that if I draw, the Earth's gravity is pulling this pen down with a force that's equal to this pen's weight, right? Its mass times acceleration of gravity. Well, Newton's third law tells us that not only is the Earth exerting a force on the pen downward towards the Earth, but the pen is exerting an equal force on the Earth up towards the pen, equal and opposite. And so every object that the Earth pulls towards it with its gravity, those objects pull the Earth towards them. But because the Earth is so massive, right? That Earth is so massive that the resulting acceleration is really tiny. So the force that this pen is exerting on the Earth yields a negligible acceleration because the mass of the Earth is so large. Where the mass of this pen is much smaller, so that same magnitude of force can generate an acceleration equal to 9.8 meters per second squared. Right? So that's Newton's third law. For every object, for every force, there's an equal and opposite force. So every force in the universe has what's called a reactionary pair. Or there's another force, per Newton's third law, somewhere that's equal and opposite to that force. So there's no unpaired forces in the universe. Every force, there's an equal and opposite force acting somewhere. So that's Newton's third law. So we can use Newton's third law to gain some insight as to the forces that act on an object. So we're going to look at, say, an object, a block, that's resting on the surface. Now, what I'm also going to do here is show how to draw free body diagrams. So this block, resting on the surface, we're going to define our coordinate system. Which way is positive and which way is negative. I'm going to say this way is the positive x direction and this way is the positive y direction. Now to draw a free body diagram of this object, I could represent it as a point, and we'll draw the forces that are acting on it. So this object, let's say, has a mass m. So what forces are acting on it? Well, it has weight, right? Because it has mass. And so its weight acts downward. It's equal to its mass times the acceleration due to gravity. Is that the only force that's acting on this object? Well, if it was, then there would be a net force, right? There would be an unbalanced force downward equal to its weight. And Newton's second law would tell us that it would be experiencing an acceleration downward. So if this was the only force acting on it, the force would be mg, and now it would equal its mass times acceleration, so it would be experiencing acceleration that's equal to, if we mass that divides out, g. It would be in free fall. It would have acceleration downward of that due to gravity. That's not happening, right? It's sitting here on this surface. So obviously there must be other forces acting on it that are counteracting that weight. And what force is that? Well, let's turn to Newton's third law. If this object is being pulled down by its weight, by Earth's gravity, that means that this object is pushing on the surface it's resting on. And if this object is pushing on the surface it's resting on, then Newton's third law tells us that the surface exerts an equal force back on the object in the opposite direction. And so the surface exerts a force that's equal and opposite. Now, in this free body diagram, it's important to note that we're only drawing the forces that act on the object of interest. So it's only this block. So yes, this block exerts a force down on the surface, but we don't draw that force because that's a force that the block itself is exerting, not a force being exerted on the block. But, per Newton's third law, the surface exerts a force back on the block, so we draw that force, and we call that force the normal force. Now it's a little bit confusing. It looks like it's N from Newton. But the textbook uses this notation where it's N for normal force. Why is it called a normal force? Just quickly, because it's always normal or perpendicular to a surface. So the surface that the force the surface exerts on this block is up, perpendicular to the surface. If the surface was tilted and the block was here, weight is always straight down. Weight is always straight down. It's never in some other direction. It's always straight down towards the center of the Earth. But the normal force exerted back is perpendicular to the surface. Normal is another word for perpendicular. So that's why it's called a normal force, because it's always perpendicular. And so technically, whenever I push against this whiteboard, I'm pushing against the surface pushes back against me. That's the normal force. The surface, this whiteboard is exerting a normal force on my fingertips, and that normal force is perpendicular or normal to the surface, so it's coming out of the board. All right? And so it's always perpendicular to the surface. Now, because this object, oh, I just erased my object, because this block is not moving, it's at rest, we know that its acceleration is equal to 0. So the net force must also equal to be 0 per Newton's second law. Right? If A is equal to 0, then F net equals to 0. And there's no other forces acting on this that we know of. It's just sitting there. So that tells us that it's not accelerating. That means that these forces must be balanced. Now, so we add the normal force plus the weight, they must equal 0. Now these are vectors, right? And so because the weight points downward, we can't just say, oh, it's plus, it's minus, right? Because it's in that direction. We're going to give it that negative sign because we said up is positive, so down is negative. So the normal force minus mg equals 0. We see in this case the normal force is equal to the weight, right? Because they're in balance. So right now, as I stand here, I'm not accelerating because my weight is acting downward, the force due to gravity on me, and the ground, the floor, is exerting a normal force up on me that's equal in magnitude, the opposite direction as my weight, and so it's counteracting my weight, so there's no net force acting on me, and I do not accelerate. Okay. So by using Newton's third law, we kind of see that surfaces must be exerting forces back on objects. And that force is called the normal force. That's the force that surfaces exert on objects whenever objects exert forces on surfaces. And this is a free body diagram where we draw the object as a point, or we could draw the object as the object itself. and draw the forces in here, sometimes it gets a little bit cluttered. Sometimes we do that, or sometimes we represent the object as a point. It's a free body diagram. Okay. So, now, let's look at a different situation. Let's say we have an object of mass m resting on a surface. Alright, so we know that the forces acting on it are, let's say, saying that's positive x, up is positive y. It's weight, mg, there's a normal force acting perpendicular to the surface. Now let's say we push it with a force P. So now, since we're pushing it, the force is directed in that direction. The push P is pushing the object that direction. Let's say the object doesn't move. Like if there's a big cardboard box full of books on the floor, and I push it, it doesn't necessarily move, right? If I push it, it can still sit there at rest. That means that there must be some force that's counteracting the push. Because if not, there would be a net force in this direction, and there would be an acceleration in that direction, right? The net force in the x direction, which is the horizontal direction, would be P, which equals ma. Its acceleration would be P divided by n. You would experience an acceleration this way. That's equal to this force divided by its mass. But that's not happening. It's at rest. So what force is opposing this force P, this push? Well, it's another force that the surface is exerting on the object. So the surface is exerting a normal force, but the surface is also exerting, I'm going to draw it here, a frictional force. It's friction. Okay? And so the textbook uses a lowercase f to represent friction. And so there is a force, frictional force that opposes it. And because it's at rest, we know that acceleration is equal to 0. So the net force in this direction must be 0, so P minus F equals 0, P equals F. So that friction equals the magnitude of that push. They're opposite directions, right? That's Newton's third law, tells us they're opposite directions, but they're same in magnitude. So if I'd stop pushing, what happens to the friction? There is none. That friction develops as a result of me trying to move it, pushing it. The friction develops because friction is a force that resists motion. It resists the onset of motion. Well, that's a type of force, a type of friction called static friction. There's two types of friction. Static friction is a frictional force that resists the onset of motion. So it only exists whenever the object is not moving, not sliding. And so the frictional force is always a force between two surfaces in contact. Okay? So here, the surface of the block, the bottom of the block, and the surface it's resting on, those are the surfaces that the friction exists between. And if I try to push it with a force P this way, then a static frictional force of equal magnitude develops that way. And the harder I push, the larger this static frictional force becomes to counteract it, to keep it in place, because static friction, that's what it wants to do, keep it in place. So if I push it with a force of 5 newtons, and if it's not moving, that means that the static frictional force is equal to 5 newtons, directed in the opposite direction. However, we know that if we push something hard enough, we can get it to move. It starts moving. And so that means that there is a maximum value of static friction. And we'll talk about friction more later, but static friction, it's surface dependent. Depending on the surfaces, that determines how much static friction there is. Like like if you step on ice, like there's definitely less friction on ice than there is concrete. Right? You can slip, you can slide much more easier on ice than on concrete because there's less static friction. So the amount of static friction that's present is surface dependent. But what happens if you exert a force that static friction it overwhelms static friction? Well, the object starts to move. And whenever an object's moving, it's sliding. It's no longer static friction. It becomes kinetic friction. Kinetic friction is a frictional force that resists motion. So it's already moving, but it acts in the direction opposite of the motion. So here, if I'm pushing a P, and let's say it starts moving, it has a velocity V in that direction, then a frictional force develops that opposes that motion. Now, this frictional force, this kinetic frictional force, isn't necessarily the same magnitude as this force P. It's constant, where the static frictional force, it varies. The harder I push, the larger the static frictional force, until it reaches its maximum. Kinetic friction is just constant. As long as it's moving, that kinetic friction is present. And so, let's say if the object is moving this way and it has an acceleration of A, then if we look at the net force in the x direction, we get P minus the kinetic friction equals NA. We can find what the value of that friction is with the magnitude of that frictional force, and I made A positive because it's in that direction, which is the positive direction I erased my coordinate system. So the push this way minus the kinetic friction that way equals the mass of the object times its acceleration. And so solving for the kinetic friction, we find the kinetic friction is equal to the push minus the object's mass times acceleration. It tells us how much friction is present. Now let's say it's moving and then we stop pushing it, right? Then what happens? Well, now this is 0, right? And friction, kinetic friction is still going to be there because it's still moving. As long as it's moving, as long as there's motion, there's going to be kinetic friction. So what happens is the acceleration changes direction. It's now pointing that way because the net force is only in this direction. So the net force is negative F, which equals MA. So A has to be negative 2. And what happens is, if it's moving this direction, that's why the friction always points in the opposite direction it's moving. So it's moving in that direction, so the kinetic friction points that way, because kinetic friction resists motion. It generates, if only friction is present, it generates an acceleration this way, and notice that the acceleration is in the opposite direction as the velocity, so it's going to slow down. And eventually it comes to a rest. And once it comes to a rest, then kinetic friction disappears. No longer there because it's not moving. And as long as nothing's pushing on it, trying to get it to move, there won't be any static friction either. So that's why things slow down to a rest, because of friction. If it's moving in this direction, friction develops, kinetic friction develops in that direction, which causes an acceleration. If we want to keep it moving at a constant speed, say if we want to keep it moving in this direction at a constant speed, then we have to exert a force on it to overcome friction. And if it's a constant speed, then acceleration is equal to 0. And so the push minus friction must equal 0. So the push must equal the friction. It must be equal to negative friction. It must be the same magnitude, opposite direction. So we have to push it the same amount of force as the kinetic frictional force. If we do that, it'll move at a constant speed. If we push it a little bit harder, that means that P will be a little bit larger than F, and it'll develop a small acceleration in that direction. If we push it a little bit softer, that means kinetic friction will be slightly larger than the push, and it'll develop a slight acceleration in that direction, and it'll start to slow down. Okay, so that's friction. We talked about kinetic and static friction. And we introduced free body diagrams. So free body diagrams is where we draw the object and draw all the forces that are acting on that object. That allows us to kind of graphically represent what's going on, and so we can see what's happening. And with Newton's second law, you can apply Newton's second law in both directions of your coordinate system. Say this is x and this is y direction. If you do the net force in the x direction, so that all the forces acting in this direction, add them up, that equals the mass of the object times its acceleration in the x direction. And also, the net force in the y direction is equal to the object's mass times its acceleration in the y direction. So you can apply Newton's second law to each direction independently. Okay. So that concludes our lecture for Chapter 3. Chapter 3 is explaining motion. I have several examples from the textbook that could be found below in the example problems, where we apply the problem-solving method to solve problems using force, weight, mass, and friction, and incorporating Newton's 3 laws. Thank you very much.